Okay, so hi everybody, welcome back. Today we're going to be continuing our chapter 14 lecture on oscillations, and I thought I would start with an example problem for you guys to work out. So here we have a graph that shows the position as a function of time of a simple harmonic oscillator. The form of the general solution is shown below, so we know that x as a function of time is equal to a cosine omega t plus phi. So that's the general form. Now, based on this, what is the phase angle phi in this case? In other words, use the information on the graph to try to figure out the phase angle phi. So pause the video, see if you can get this, and then come back to it when you think you have your answer. Okay, so we'll start by writing out the general solution. X as a function of time is a cosine omega t plus phi. So if we plug in t equals 0, what we get is the initial position, which is x when t is equal to 0. What we get is a times cosine. Omega t is now 0, so this is just cosine of phi. Now, from the graph, we can actually see what the initial position is. It's up here. X, when t is equal to 0, is equal to the amplitude. In other words, we're at the maximum displacement when t is equal to 0. So then what we can do is sub that in for x at time 0, and that gives us a equals a cos phi, which means cosine phi is equal to 1. So basically, we need to figure out what angle, when I take the cosine of it, do I get 1. So to figure this out, we can go to the unit circle, and we'll recall that cosine of an angle is equal to x on the unit circle. So let's draw the unit circle with the x and the y axes like so. And okay, the radius of this circle is 1, by the way. So only when we're at this point on the unit circle is x equal to 1. There's actually no other point that works. And what is the angle in that case? Well, it's actually 0. So the phase angle in this example is equal to 0. Okay, that's how you do this one. Okay, so here's another example. We have a graph, again, showing the position as a function of time of a simple harmonic oscillator. What is the phase angle in this case? So again, pause the video, see if you can work this out, and then we'll do it together. Okay, so we'll start with the same general form as before. X of t is equal to a cosine omega t plus phi. And so if we plug in t equals 0, again, we get the initial position out of that, which says x at time 0 is equal to a cosine omega t is 0, so we are just left with phi inside the cosine function. And from the graph, we can read off the initial position. So x when t is equal to 0 is 0. So here we have, on the left side, 0 equals a cosine phi, which means cosine phi equals 0. Okay, so just like before, we remember that cosine of an angle is equal to the x coordinate on the unit circle. So let's draw the unit circle. Okay, so we want x to be equal to 0. Well, that happens actually at two different points on the unit circle. One of them is up here on the y-axis. That's where x is equal to 0, but also down here. So essentially, we have two possible angles. One of them is this one, which is an angle of pi over 2 radians, or 90 degrees. This one is 3 pi over 2, or 270 degrees. Now, these are both possible, so we don't really know the answer until we do some more work. So phi is equal to pi over 2, or 3 pi over 2. We don't know which one is correct yet. We need to test each possibility. Okay, so actually, let's go back to the graph. We'll remember that velocity is equal to dx dt, which is equal to the slope of this graph. So if at t equals 0, I draw a tangent line to the curve, I can see that the velocity at time 0 is something positive. I don't know the actual numerical value for the initial velocity, but I do know that it's positive. Okay? So what we can do is figure out which one of these two angles will give us a positive initial velocity. Okay, so if x of t is equal to a cosine omega t plus phi, then v as a function of time would be the derivative of x with respect to time, which would be, okay, we take the derivative of cosine, we get minus sine, but then we need to take the derivative of what's inside the cosine function with respect to time. So the derivative of omega t plus phi with respect to time is just omega, because omega and phi are both constants. And so if I plug in 0 for the time, I get minus a times omega times sine of just phi, because we're setting the time equal to 0 here. So if phi is equal to pi over 2, okay, if we plug in pi over 2 for the angle, the sine of that angle is actually equal to 1. So the initial velocity is just minus a times omega. If we plug in the other angle, 3 pi over 2, sine of 3 pi over 2 is minus 1. So we'll get a minus 1 times minus a omega, which is plus a times omega. Okay, so one of these is negative, the other is positive. Remember, the initial velocity is supposed to be positive, which means we can rule out that first angle, pi over 2. Okay? This is the correct one. So therefore, phi is equal to 3 pi divided by 2. Okay, that's how you do this. Okay, so we've already spent a lot of time talking about a horizontal mass spring system. So I'm talking about a spring connected to a mass, which maybe can slide back and forth horizontally on, let's say, a table. We already know how to deal with that situation. We spent most of the last video talking about this. So what then happens if the system is oriented vertically? So instead, now we're going to have a spring oriented vertically like this with a block connected to it. If we set this system into simple harmonic motion so that the block oscillates up and down, it's natural to wonder if that will behave any differently than the horizontally oriented mass spring system. Because there is a difference. Notably, we have gravity acting in the vertical direction in this case. Does that change the behavior in any way? Well, let's figure it out. So the general problem we're looking at is we have a vertically hanging spring, and right now there's no mass attached to it in this leftmost picture. So it's at its relaxed or natural length hanging in this orientation. So we'll say y is equal to 0. But then when we put a mass on the end of it and allow it to hang vertically at rest, we'll see that the spring has stretched out by some amount. And it's stretched out by an amount which I'll call YEQ once we add that hanging mass. By the way, for this derivation that we're going to do, I'm going to have the y-axis pointing down. So just keep that in mind. And so if I want to figure out how much the spring has just been stretched out, I can apply Newton's second law to the vertical direction. So we have the net force in the y direction is equal to m times ay. And there are two forces to worry about here. We have the force of gravity pointing down, and then we have the spring force pointing up, like this. So if the block is not moving, then I can set ay equal to 0, and then we'll have Fg pointing down, which is the positive y direction according to the coordinate system that I set up here, and then minus Fs, which is pointing up, and the negative y direction, and those two equal 0. So basically, the magnitude of the force of gravity and the magnitude of the spring force have to be the same in order for them to balance out and for the block not to be moving. Well, the force of gravity, of course, is just given by m times g, whereas the magnitude of the spring force is given by k times the amount it stretches out, which in this case, we're using YEQ to denote that. So we have mg minus k times YEQ is equal to 0. So if you solve for YEQ, you'll get YEQ is equal to mg over k. So the point of this is, when you add this mass to the end of the spring, it's now stretched out by some amount, and the new equilibrium position is given by mg divided by k. That's the new position where the force, the overall force acting on the block is going to be equal to 0. Okay, so that's what it looks like when the block is at rest and it's just hanging there statically. Now let's consider the case where the block is set into motion. So for example, we could pull the block down further away from that equilibrium position and then let it go. So now it will be bouncing up and down like this. So that's what we want to think about. The block is now set into motion. So we'll still use the net force in the y direction is m times ay, just like before. But now we're not going to simply say acceleration is equal to 0, okay? Because it's not, in general, going to be 0 anymore. So we have mg minus k times y. That's the sum of the two forces, which is gravity and the spring force here. That equals m, which is the mass of the block, times ay, which, by the way, is the second derivative of y with respect to time. That's how we denote acceleration. Okay, the next thing we're going to do is a little bit of a trick with our coordinate system. We're going to shift our coordinate system so that the equilibrium position YEQ is now the 0 point of the coordinate system. Okay, so before y was the coordinate, now we're going to use a new coordinate, which I'll call y prime, where y prime is equal to y minus YEQ. From before we saw YEQ is mg over k. Okay, so in other words, just apply this shift in coordinates to the equation we have above. So we have mg minus k times y, but using what we just said, y is equal to y prime plus YEQ, so that's going in for y here. that equals m times the second derivative with respect to time of y, which again is y prime plus yeq. So we have mg minus k, y prime plus mg over k, because this is what we found for yeq. And then on the other side of the equation, if we think about it, yeq is just a constant. So if I take its derivative over here, I'm just going to get 0. And the only thing I'm going to be left with is m times the second derivative of y prime with respect to time. Also notice something that's happening on the left side here. I have positive mg, and then if I distribute minus k into here, I'm going to have minus mg. So in other words, this term and this term will cancel, simply leaving me with minus k times y prime over here is equal to m times the second derivative of y prime with respect to time over here. So I can rearrange that to say, basically by adding k times y prime to both sides, putting it over here, and then dividing by m on both sides, I can get the second derivative of y prime with respect to time plus k over m times y prime is equal to 0. In other words, this is a differential equation that describes simple harmonic motion around an equilibrium position where the angular frequency omega, that's the term, remember, that goes right here in front of the position variable, omega squared is given by k over m. So the point of doing all this is to say that if we have a horizontal mass spring system that oscillates this way, or a vertical mass spring system that oscillates this way, we end up at the end of the day with the same exact differential equation that describes the motion with the same exact angular frequency that describes how fast the motion is happening. So therefore, the takeaway point is a vertical mass spring system behaves just like a horizontal mass spring system. They both undergo simple harmonic motion about some kind of equilibrium position. In this case, we oscillate horizontally around that equilibrium point. In this case, we oscillate vertically around that equilibrium point. The only difference is that in this vertical case, the equilibrium point that we oscillate around is shifted down a little bit. But other than that, it's the same exact motion. So we have the same general solution, which is given by position x as a function of time is a cosine omega t plus phi, where a is the amplitude, omega is what we call the angular frequency, and then phi is that phase angle from before. And in both cases, omega, the angular frequency, is simply given by the square root of k over m. Okay, so from here on out, we can treat these two situations as essentially the same thing. Okay, so next, let's talk about energy in simple harmonic motion. What we're going to do here is apply some of those ideas that we developed back in chapters 7 and 8, dealing with energy, and apply them to a simple harmonic oscillator. In particular, we're going to be thinking about the mass spring system. Okay, so how do we sort of quantify the energy of a simple harmonic oscillator? Well, remember that the total mechanical energy, E, of any system is just the sum total of kinetic and potential energies. So in other words, E is equal to K plus U. Okay? Now remember, the kinetic energy has to do with the motion of the system. So in this case, we have a block that's moving back and forth with some velocity. The kinetic energy is going to be given by 1/2 mv squared, where m is the mass of the block and v is the velocity of the block. On the other hand, the potential energy is going to have to do with the spring, and in particular, how much energy the spring is storing because of its compression or its stretching. So U, the potential energy, is going to be given by 1/2 times K times x squared, where again, X is the amount of stretching or compression in the spring. So if we add these two terms together, we get the total mechanical energy of the simple harmonic oscillator. So assuming that there aren't any non-conservative forces like friction or air resistance that act on the system, we know the total mechanical energy is going to be conserved. And if your mechanical energy is conserved, that means your system is not losing mechanical energy over time as it oscillates. And that means the motion will just happen indefinitely. It will continue forever, oscillating back and forth. Now, in reality, we are going to have friction and air resistance acting on any real system, so it will gradually lose energy over time, and the oscillations will actually die out. And so what we'll do in the last video of this lecture is see how to deal with that. How do we actually deal with losing energy in simple harmonic motion? But for now, we're going to assume that energy is not lost and we don't have forces like friction or air resistance. And again, in those cases, the motion will just continue indefinitely. So the next thing I'd like us to take a look at is how can we use the results of the previous video, the position and the velocity functions that we derived, to say something about energy in a simple harmonic oscillator. So here's what we're going to do. We're going to take x as a function of t. Remember, the general solution for this is a cosine omega t plus phi. And v as a function of t, this is our velocity function, is given by minus a omega times sine omega t plus phi. Using these previous results, we can show that 1, the total mechanical energy of a simple harmonic oscillator is conserved. 2, we can express that total mechanical energy E purely in terms of the amplitude. So we're going to derive this equation. E is equal to 1/2 k times a squared. And then finally, E can be expressed purely in terms of the maximum speed also. So the total energy also can be written as 1/2 times m times v max squared. So we're going to prove all these results. Let's get into that. Okay, so we're going to start with the following. The total mechanical energy, E, is equal to the kinetic energy K plus the potential energy U. So here, total mechanical energy equals kinetic energy plus potential energy. That's what that says in a nutshell. So E, therefore, is equal to 1/2 times mv squared plus 1/2 kx squared. And we'll recall that for x as a function of time, this is generally given by a times cosine omega t plus phi. And for v as a function of time, it's just the derivative of x with respect to time, which comes out to minus a times omega sine omega t plus phi. So how about we take those functions and plug them in here for v and here for x and see what we get. Okay, so we'll have E equals 1/2 times m. Now v is going to be minus a times omega sine omega t plus phi. And we're squaring that. And then I add 1/2 times k. X is given by a cosine omega t plus phi. And we're squaring that. Okay. So there's a common factor of a squared in both of those terms. So I'm going to pull that out. So we have 1/2 times a squared in both terms. The first term is going to have m times omega squared as the constant out front, times sine squared of omega t plus phi, but I'm not even going to bother writing that. I'll just write dot, 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 but you know that's omega t plus phi inside of the sine function. And for my second term, 1/2 a squared is multiplying k. So there's just a k in front of cosine squared. Again, omega t plus phi is what goes in the cosine function. So the next thing we'll do is remember that omega, by definition, is the square root of k over m, which means omega squared is k over m, which means m times omega squared is equal to k. So in other words, this factor of m times omega squared in front of the sine function is just equal to k. So in reality, what we have is e equals 1/2. There's a common factor of k, which I can pull out from both terms, multiplying the a squared. And once I do that, I have sine squared plus cosine squared of omega t plus phi is what is going inside of each one of those functions. But it actually doesn't really matter because the trig identity we're using here is that sine squared of an angle, let's call it beta, plus cosine squared of that same angle is always equal to 1, regardless of what the angle beta is. So because of that, in the brackets, we simply have 1. So that proves the first result, that the total mechanical energy, E, can be expressed as 1/2 Ka squared purely in terms of the amplitude. Now, K and A are two constants, so this implies E is a constant as well. In other words, if E is a constant, it's not changing over time, the total mechanical energy is conserved. And of course, in doing this derivation, we assumed at the outset no friction, no air resistance. Okay, so what else can we do with all this? Well, we can remember here, starting with the result we just derived, E is equal to 1/2 Ka squared. We can remember from just a second ago that K is equal to m times omega squared. Okay, so E therefore is equal to 1/2 times m times omega squared a squared, or I could write this as 1/2 times m times a times omega quantity squared. Also recall from the previous lecture, from the previous video, we derived V max, the maximum speed of the oscillator, is equal to A times omega. So therefore, I can write the total mechanical energy E is 1/2 times m times V max squared. Okay, so that proves the other result. So we can write the total mechanical energy as 1/2 Ka squared in terms of amplitude, or 1/2 m V max squared in terms of the maximum speed. These are the same thing. Okay, now just as a bonus, I'm going to take this one step further for you guys, all right? So E is equal to, again, K plus U. And we can write this as 1/2 m times Vx squared plus 1/2 times Kx squared. Now remember that Vx is nothing more than the first derivative of x with respect to time. So really, the kinetic energy can be written as 1/2 times m times the first derivative of x with respect to time squared. And then we add to that 1/2 k times x squared to include the potential energy. Now, if energy is conserved, I should say if mechanical energy is conserved, there's a lot of ways we can write that, but one way is this: dE dt is equal to 0, meaning it's not changing over time. Okay, if it's conserved, then the derivative of E with respect to time should be 0, is the idea. Okay, well, how about we take this formula, or this expression for the total energy, and take its derivative with respect to time. So we have to be a little bit careful in how we do this. So in my first term, I'm going to have 1/2. So if we're taking the derivative of E with respect to time, my first term is 1/2 times m. Okay, then I take the derivative of dx dt squared. So since dx dt is being squared, by the power rule, I pull out a factor of 2, and then I have dx dt to the first power. But I'm not done yet, because I need to take the derivative of what's inside of there with respect to time. So if I'm taking the derivative of dx dt with respect to time, that would be the second derivative of x with respect to time. So that's the derivative of the first term. Now I'll do it again for the second term. I have 1/2 times k as a constant out front. And then I have x squared. So I would take 2 times x to the first power. But then again, I have to take the derivative of x with respect to time, which is dx dt. By the way, what I'm doing here is called the chain rule to properly evaluate that derivative. So let's try to clean this up a bit. So in my first term, I simply have m times the second derivative of x with respect to time times the first derivative of x with respect to time. In my second term, the 2 cancels with the 1/2. I have k times x times the first derivative of x with respect to time. And I want this to be 0 to indicate that the energy is not changing over time. So what if I divide out dx dt? Basically, I just get rid of it here and here. I still have 0 on the right-hand side. And so we're left with m times the second derivative of x with respect to time plus k times x equals 0. Now, hopefully this is starting to look familiar. I can write this as the second derivative of x with respect to time. Divide out the m. This is k over m times x equals 0. If we define omega to be the square root of k over m, then I have the second derivative of x with respect to time. K over m would be omega squared times x, and that would equal 0. So this is the differential equation for a simple harmonic oscillator that we found in the previous video. So we can also get this equation using energy methods. Okay, that was the point of doing this. Okay, so the idea is that although the kinetic and potential energies of the simple harmonic oscillator will be individually changing over time. The sum total of those two is going to remain the same. So to give you a sense of what this looks like, I'm going to show you an animation. So we have a block connected to a spring, and the block will oscillate back and forth on a frictionless table without any air resistance. And as that happens, we're going to be plotting out the potential energy U, which is 1/2 kx squared. So this is going to be a parabola that's concave up like this. We're also going to plot out the kinetic energy, which, as it turns out, is going to be this concave down parabola. And the total, E, is just going to be a flat line indicating that this is a value which is not changing. Okay, and by the way, we're plotting these energies against x, against the position of the block. So minus A to A would be the range of positions that the block will take on. Okay, so let's take a look at this. Okay, so the first thing to notice is that at the turning points of the motion, which would be minus A and plus A, that's where the block is actually turning around, the potential energy is at a maximum and the kinetic energy goes to 0, which makes sense. The block has to momentarily come to a stop in order for it to turn around. And that is also the time when the spring is being maximally compressed or maximally stretched out, which is when we'll have the most potential energy. On the other hand, at the equilibrium point, x equals 0, which is right in the middle of the motion, there's no potential energy because 1/2 kx squared is going to be 0 if x is equal to 0. So in terms of potential energy, we'll be down here. But the kinetic energy will be at a maximum. In fact, all of the energy is going to be in the form of kinetic energy when we're at x equals 0. And that's what's being shown in the graph. So again, although individually K and U are going to be changing, kinetic and potential energies are individually changing, the sum total E is remaining the same. Okay, that's what we're seeing here. By the way, I took this animation from the link that's shown here, so if you'd like to watch that again on your own time, you can access the link through Canvas. Okay, so let's do an example. Here we have a simple harmonic oscillator, which consists of a block with a mass m equals 2.43 kilograms, and a spring with a constant k equals 221 newtons per meter. At t equals 0, the displacement of the block x is 0.0624 meters, and the velocity of the block is Vx equals positive 0.847 meters per second. So we're going to find the equation for the motion using energy methods. In other words, remember the general solution, x of t is a cosine omega t plus phi. We're going to find the constant a, we're going to find the constant omega, and we're going to find the constant phi. So you may notice we already did this problem in the previous video. We're going to go through it again, this time using energy methods. So let's see how this works. Okay, so the first thing we're going to do here is solve for the amplitude of the motion, which is A, capital A. And so the way we're going to do this is to just write down the definition of total mechanical energy. E is equal to K plus U. And so let's make some substitutions into that. Remember, if we want, we can express the total mechanical energy as 1/2 Ka squared. So this is the total mechanical energy expressed in terms of amplitude. So that's E. On the other side of the equation, we have the kinetic energy, which is 1/2 m Vx squared, and then the potential, which is 1/2 k x squared. So basically, we need to know both Vx and x at some moment in time. Well, the thing is, we do know the values for t is equal to 0. So at t equals 0, we have x is 0.0624 meters, and we have Vx equals 0.847 meters per second. So those are the values of Vx and x that we're actually going to use. And so if we solve for a squared in that equation, basically on both sides multiply by 2 over k, we're going to have m divided by k, Vx squared, plus x squared. And of course, if we want to find a, we should square root both sides. So the amplitude is going to be the square root of m divided by k. So the mass is 2.43 kilograms divided by k, which is 221 newtons per meter, which is a kilogram per second squared, multiplied by Vx, which is 0.847 meters per second, and we have to square that, and then add that to x squared, which would be 0.0624 meters squared, okay? So if you work this out, it's going to come out to 0.1085 meters, or to 3 sig figs, 0.109 meters. So that's the amplitude. We're going to need that. Another constant we're going to need to know, by the way, is omega. Omega is the square root of k divided by m. So it's going to be the square root of 221 kilograms per second squared divided by 2.43 kilograms, which works out to 8.537 radians per second, or 8.54 radians per second when we round to 3 sig figs. Okay, so that's what we get when we solve for angular frequency, by the way. So we've got the amplitude, we've got the angular frequency. The only thing left to do is solve for the phase angle. Which is phi. Okay, so there are a couple different ways we can go about doing this, but let's just remember the general solution, x of t equals a cosine omega t plus phi. And if we plug in t equals 0, we get a times cosine omega times t is 0 now, and we just have phi inside the cosine function. So cosine of phi is going to be x at time 0 divided by a, which in this case, what's x at time 0? That's this number right here, 0.0624 meters. And then what's a? That's the amplitude. That's 0.1085 meters. So what does that work out to? That's 0.5751. So in other words, cosine phi is 0.5751. So we want to know what phi is. So to get it, we'll take the inverse cosine of 0.5751. And if you punch that into your calculator, it will tell you that the answer is 54.89 degrees. So this is the result the calculator will give. Now, unfortunately, we're not done yet because the calculator doesn't give us the whole story. Let's remember what cosine really means in the first place on the unit circle. Cosine of an angle is equal to the x-coordinate on the unit circle. So if we draw that unit circle with x and y coordinates, what we're saying is we're going to take x to be 0.5751. Okay, so if you think about it, there are actually two different angles that will work. This angle up here, which is the one that the calculator gave us, 54.89 degrees, that will work. But also, what the calculator did not tell us is the negative of that angle also works. So minus 54.89 degrees will also work. So we actually need to decide between these two which one is correct. So here, we're going to test out the two possibilities, so plus or minus 54.89 degrees, to see which is right. We don't actually know which one is right. So the way we're going to test this out is by using the velocity function. So remember, velocity as a function of time is minus a times omega sine omega t plus phi. And if we plug in 0 to that function, we get minus a times omega sine of phi. So here's the idea. Plug in positive 54.89 degrees. And here's what you'll get. Sine of 54.89 degrees is something positive, but there's a negative sign out front, so this comes out negative. On the other hand, if we choose the angle of minus 54.89 degrees, if we plug in sine of minus 54.89 degrees, you'll get something negative. And there's a negative sign out front, so you'll end up with something positive. Now the velocity at t equals 0 should be positive, right? So the angle that gives us a positive velocity is the one we want. So this is correct. This works. This one does not work. So in other words, the answer the calculator gave us was wrong. It's this one that we had to do a little bit of extra thinking to see was even a possibility that is correct. Okay? So let's convert this to radians real quick. We have minus 54.89 degrees. If we multiply that by 360 degrees is equivalent to 2 pi radians. That's the conversion factor. This will give us 0.958 radians, which means the full solution is A, which is 0.109 meters, times cosine, omega, which is 9.54 radians per second, times t, and then there's our phi, minus 0.958 radians. So we converted to radians, by the way, just so we have consistent units of radians inside of that cosine function. And so that is the solution. Same as what we got before. Okay, this time using a slightly different method. Okay, so let's take a look at another example dealing with energy in simple harmonic motion. this says, what is the displacement x of a simple harmonic oscillator at the moment when half the total energy is potential and the other half of the total energy is kinetic? So in other words, there'll be some position, there's some value of x where half of the energy is in the form of potential energy and the other half is in the form of kinetic energy. So we're going to figure out what that value of x is, and we're going to give the answer as a fraction of a, the total amplitude of the motion. So let's take a look at how to work this out. Okay, so we're going to start with E is equal to K plus U. That is, the total mechanical energy is kinetic plus potential. And we're going to take a statement from the problem that was, of course, put in words and try to translate that into an equation. So we're told that half of the total mechanical energy is potential. Okay, so how can we take that statement and translate it into an equation? Well, 1/2 E, that's 1/2 the total mechanical energy, equals potential, equals U. Okay, it's pretty much that simple. So, okay, let's take that a step further. 1/2 of E is the same as 1/2 of 1/2 times Ka squared, because remember, the total mechanical energy can be written purely in terms of the amplitude. Also, the potential energy is given by 1/2 Kx squared, so that's going to go here on this side. Okay, so right away we can cancel out some things, 1/2 K and 1/2 K, and we're left with x squared is equal to 1/2, because I still have this factor out front, times a squared. So x would be plus or minus the square root of 1/2 times a squared, or in other words, plus or minus 1 over root 2 times a. Okay, so in other words, if we kind of look at the x-axis, all the different positions where our mass could be, let's take this to be x equals 0, this is x equals plus a, x equals minus a. Over here, where x is equal to minus 1 over root 2 times a, and also over here, where x equals positive 1 over root 2 times a, these are the 2 points where energy is evenly split between potential and kinetic. Okay, that's what we learned. So here's an example that you can try out on your own. Actually, there are 2 questions here. The first one is, what fraction of the total mechanical energy of a simple harmonic oscillator is potential energy at the moment when x is plus or minus 3/4 a? Then we have, what fraction of the total mechanical energy of a simple harmonic oscillator is kinetic energy at the moment when x is plus or minus 1/2 a? So pause the video, see if you can work this out, and then we'll go through it together. Okay, so we'll start with the first question in this example, which is, what fraction of the total mechanical energy is potential? So that would be U divided by E. Okay, that would be potential divided by the total. That's the fraction that we're looking for. So how can I express this fraction, U divided by E? Well, U is 1/2 times k times x squared. And remember, E can be written as 1/2 times k times a squared, right? So cancel out that 1/2 k, and we just have x divided by a, all squared. Now in this case, we said x is going to be equal to plus or minus 3/4 a. So we'll take that and divide through by a, and then we'll square it. A's will cancel. We have plus or minus 3/4 squared. So if we're squaring it, it's always going to be positive. So don't worry about the negative solution. It's 3 squared on top divided by 4 squared on the bottom, which is 9 divided by 16. So in other words, if x is either positive 3/4 a or negative 3/4 a, then 9/16 of the total energy is going to be potential. So this is the fraction of the total mechanical energy that is potential energy. Okay, and that's for for x equals plus or minus 3/4 a. Okay. So the second question what fraction of the total mechanical energy is kinetic? So now we want kinetic divided by the total. That's the fraction we're interested in. So let's remember that the total mechanical energy E is equal to K plus U, which means K can be written as E minus U. So K divided by E is the same as E minus U divided by E, which would be 1 minus U divided by E. Okay, in other words, the fraction that's kinetic, which is over here, is just 1 minus the fraction that's potential, which is over here. Because, of course, those two add up to 1. So, okay, in this case, it's useful to write U as 1/2 times kx squared, and we can write E as 1/2 times ka squared, just like before. But again, since we're dealing with the fraction that's kinetic, we're doing 1 minus x divided by a, all squared, after we cancel the 1/2 k factors on the top and bottom. So in this case, we have 1 minus, for x, we're going to be putting in plus or minus 1/2 times a, and then divide that by a, and then square. Cancel out the a's. We have 1 minus plus or minus 1/2 squared. Okay, so that's just 1 minus 1 squared over 2 squared, 1 minus 1/4, that's 3/4. So what is this? This is the fraction of the total energy, total mechanical energy, that is kinetic for x is plus or minus 1/2 a. Okay, so that's how you do these two examples. So we're going to end this video here. I'll see you in the next one. We'll continue on with our chapter 14 discussion on oscillations. And next time I see you, we're going to start talking about pendulums, which is a different type of simple harmonic oscillator. So we're not going to just be sticking to the mass on a spring the whole time. We're going to look at other types of systems. So I'll see you in the next video. Until then, as always, be safe out there, be healthy, take care.